In the first two lectures on noise, we looked at where noise came from, the causes of noise, and also some of the characteristics associated with one particular noise type called thermal noise or Johnson noise. In this lecture, we're actually going to look at how we do some basic noise calculations associated with resistors and other capacitive components. In circuit analysis, we often represent thermal noise as a voltage source in series with a resistor. And the value of that voltage noise is the square root of 4 times K times T, R and B. And you'll understand why we express it this way in a second. In this expression, K is Boltzmann's constant, who was an Austrian physicist. T is the absolute temperature in Kelvin, and usually assumed to be around 300 degrees. R is the resistor that you're concerned with, and B, the bandwidth, is the range of frequencies over which you want to calculate out the noise. I use a useful rule of thumb, which is that a 60 ohm resistor at 300 Kelvin is very close to 1 nanovolts multiplied by the square root of the bandwidth. And using that figure, I can actually calculate out noise equations and analysis in my head. And this is all thanks to Ludwig Boltzmann, who established the Boltzmann's constant many years ago. So let's look at how we calculate out noise in more detail. We use the Nyquist formula. I know that many of you know about Nyquist as a sampling theorem, but Nyquist was a communications engineer and he did a lot of studies into theoretical communications. Here we have the calculation for noise voltage, and it's the square root of 4 times the Boltzmann constant times the temperature times the resistance. From this equation here, the units are always in volts per root hertz. We're not considering bandwidth at the moment, and that's why often we separate out the bandwidth in noise calculations so we can easily adjust for the effect of different bandwidths. From previous, you know that it doesn't matter what the frequency is, it only matters what the bandwidth is. And we can also express this as a noise current, which is 4kT divided by the resistance, and then take the square root of it. And current noise spectral density is always in amps per root hertz. And you can see this quoted in many data sheets that you may see for op-amps or other amplifiers. Noise always increases with bandwidth, it always increases with resistance and temperature, whereas current noise always decreases with resistance. So in any given design, you should try and keep the bandwidth as low as possible, as long as it can deal with the application, because that will reduce the noise level from your circuit. Now let's look at a practical example and do some calculations based on noise. Let's take a simple 1k ohm resistor. And we're going to look at the noise generated in a 1 Hz bandwidth at room temperature of 300 K. Plugging the numbers into the equation, we have a noise voltage, which is the square root of 4 times Boltzmann constant, times the temperature, times the resistance, times 1 Hz. And that works out to be 4.07 nanovolts RMS. If you were to apply a 1K resistor over the audio band, which goes from 20 to 20 kilohertz, which is a 19.98 kilohertz bandwidth, then the same 1K resistor would produce 575 nanovolts RMS. So in the bandwidth of 1 Hertz, it would produce 4.07 nanovolts per root hertz, but in a 20 kilohertz bandwidth, it would produce 575 nanovolts. And relating that to a noise current for the same 1K resistor, that would mean it would generate a noise current of 575 picoamps RMS over the same 20 kilohertz bandwidth. You may think from this calculations here that thermal noise is actually not very big, and you'd be correct to a large extent. Now let's apply the thermal noise that we've learned from the 1K resistor and think about it as it responds to an amplifier. We can consider noise voltages and currents to behave just like any other current sources or voltage sources within a circuit. So let's take a perfectly noiseless amplifier. We will have a gain of 100 times for this amplifier, and we'll constrain it to have a bandwidth of 20 kHz. If we connect our 1 k ohm resistor to the input and have a noise voltage source, which is 575 nanovolts, then at the output we would measure 57.5 microvolts RMS at the output of the amplifier. If you were to change the amplifier bandwidth, then it would increase or decrease the noise. And thermal noise for any given circuit is the minimum you can achieve. When you apply amplifiers, you can never make noise better, you can only make noise worse. And that's an important learning from noise analysis, is that any amplifier or circuit will always make the noise worse. You can never make it better. For certain applications, they actually cool the amplifiers down to low temperature because the temperature will reduce the amount of noise that they're generating. So far we've just looked at one resistor. Now let's look at two resistors. And first of all, let's consider two resistors connected in series. So here we have our two resistors, R1 and R2, and we have voltage source 1 and voltage source 2. How much noise do they generate? Well, we know from statistics that the noise voltages from both sources can sometimes be positive and sometimes be negative. And in the case of Vn1 and Vn2, if they were approximately the same value, then we could have Vn1 and Vn2 adding together, or Vn1 and Vn2 cancelling each other. So in this case here, our average noise power from these two add, and the noise power adds. So to calculate out the noise voltage, we need to add the square of the RMS voltages and take the square root. In other words, if we take the square of voltage source Vn1 and add it to the square of voltage source Vn2, plugging it in the Nyquist equation, we calculate out that the Vn total would equal to be the square root of 4 times the Boltzmann constant times temperature, which is the same in both instances, multiplied by the addition of the resistors, and then multiplied by the bandwidth. This is effectively the same as two resistors in series. What that's really saying is the noise from two 10k resistors in series is exactly the same as one 20k resistor. Now let's look at the same resistors in parallel. And here we have to use superposition and also the voltage divider rule. If we make Vn2 equal to 0 and Vn1 is only existing, then the output is equal to Vn1 times the resistor of R2 divided by R1 plus R2. If we then make Vn1 equal to 0 and calculate out the effect of Vn2, we get this one here. So adding those together and taking the square, we get the total output of Vn1 times the ratio of R2 to R1, and Vn2 as the ratio of R1 to R1 plus R2, which gives us effectively the result down here. And this equation here is the equation for two resistors in parallel, which you've done many times in circuit analysis. If we have multiple outputs or output noises, we can actually consider the total output is the same as having one resistor having the same resistance as the two in parallel, which is what we've already proven. It's important to realize that the temperature of all the resistors must be the same. If you have the same value of resistor and the same temperature, the thermal noise will be exactly the same. And this would stack up with common sense. If you got two different thermal noises from two 1k resistors in series than you did from a single 2k resistor, then that would suggest that somehow or other you could actually generate a power station from a resistor network, which would be a perpetual motion machine, which, much though they'd be fantastic to have, are impossible to create. In the next lecture, we'll actually look at how we go on to apply some of this noise theory into real amplifier circuits and do noise analysis of those circuits. Thank you.